Welcome to the second of a 4-video series on quadratic equations. The quadratic formula, origin story. You may recall from video 1, if you saw that, or just math classes in general, that when we're given a quadratic equation like this, the typical thing to do most of the time is to factor, set each factor equal to 0, and solve the equation. Pretty basic. No big challenge there. But here's something to consider. Suppose we were trying to solve this problem the same way, and we tried to factor. You may need to pause the video here to convince yourself, but this thing is not factorable. And therefore, what we're going to have to do is ask ourselves, what if factoring doesn't work? Well, that is where the quadratic formula comes in. What you're going to see in this video is not a how-to video. It does not show you the mechanical steps of solving a problem. This video is more of a history lesson of how the quadratic formula came to be. So, let's get started on that. The first thing that they decided to do here is add 4 to both sides. And when they added 4 to both sides, they got the negative 4 on the other side. Now this is contrary to the factoring method, but this is something that they tried. Seems logical. Now the next thing they did is add 25 to both sides. And this would make no sense to the average person. And remember, this is not a how-to video, so I'm just sharing some history with you here on how equations like this were solved. Keep that in the back of your mind. Why on earth would they add 25 to both sides? Well, nonetheless, they did. And what ended up happening is they thought, well, maybe we'll be able to factor now. And it turns out the left side of this equation is factorable. And not only factorable, but factorable into two identical factors, which they then wrote as a perfect square trinomial. And then, because they had something squared equals 29, they were allowed to apply what's called the square root property of the equation, which brings the squared to the other side as a square root and giving us two roots, the positive and the negative root. And then in order to solve for x, they would subtract 5 from both sides to get x by itself. And what ended up happening is they ended up solving the problem using a non-factoring method. Well, here's some historical logic. Because they chose to add 25 to both sides, and I still haven't addressed why they did that specifically, but because they chose to add 25 to both sides, they got two identical factors here. Two identical factors were expressible as a square of a binomial, and that's what led them to be able to use the square root property and isolate x. But of course the real question is, why did they choose 25? Well, they discovered that there'd be a magic number that they could use, and it wasn't always 25, but it depended on the 10x. And what they discovered is if they took half of this number and squared it, that would be sort of the magic number that they would have to add to both sides to make this entire process work. Notice, by the way, when I mean half squared, half of 10 is 5, and that squared is 25. Again, you won't be expected to do this, although you could, certainly. But it's a bit of a history that's going to lead us up to understanding where the quadratic formula came from. So, here we have an equation and a solution. And before we go on to more generalities, and before I give you the origin story of the quadratic formula, let's remind ourselves what the plus or minus means in case it's been a long time since you've seen this. The plus or minus means that there are two roots to this equation, one with a plus in that place and one with a minus. So it turns out that these symbols represent two different answers to the to this particular quadratic equation. By the way, radical 29 is a decimal, and when I worked each of these out on a calculator, I got decimal versions. Now, that's not what you would do in an algebra class, but it's always helpful to remind you that the two answers to these are actual real numbers in this case. Okay, so what does it mean to say that these two numbers are solutions to this equation? Well, let's just take one of the solutions and use it to prove a point. If that's a solution to this equation, shouldn't I be able to plug that back in for x and have this whole thing on the left side equal to 0? Well, that's exactly what I did. I put big open spaces where the x's are. I plugged in this particular root, and I did a lot of algebra. And it's not the point of this video other than to say that when I worked out all this algebra, I did in fact get 0. Again, this isn't what you would necessarily do in a math class, but this slide shows you what would happen if we actually plug this in. It really is a root to this equation, as is the other one that I did not plug in. But back to this problem. What if we were going to solve this kind of problem over and over and over again? Would we really want to go through that same procedure each time? Well, historically, that's not something that they wanted to do. You know, for example, what if we had to solve this problem and this one and all of these problems here? Well, they all look very similar, and they could all be done by the same procedure. But would you really want to do that? Well, historically, they certainly didn't. And one thing they realized is, in all these problems, that only two things change from problem to problem. Whatever this number is, and whatever this number is. Nothing else changes. And so somebody thought to themselves, why don't we come up with a generic equation that represents all of those at the same time? Remember, the only thing that changes from problem to problem is there's a number here and a different number here. So they decided to let M and P, just two randomly chosen letters for no reason, represent whatever numbers might be in those two slots. And they came up and they asked themselves the question, could they do the exact same process that we just saw using M and P instead of actual numbers? And it turns out they did. So now what you're going to see is a mimicking of the exact same process you saw when M and P were numbers specifically. So we'll bring the P to the other side, and then we will add, or they added, I should say, this strange quantity to both sides. Well, this is like the 25 in the last problem. It came from half of this quantity squared. So after adding that strange quantity to both sides, they did this, and they realized, the thing on the left is not only factorable, but factorable into the same two factors so that we can write it as a square, use the square root property, and then subtract m over 2 from both sides. Now this algebra I just went over very quickly. It's not something that your professor or teacher would necessarily expect you to do, but what it does show is that you can do the exact same process that we did when the problem had numbers to the problem that has an m and a p where those numbers were. So what does this formula mean? Well, let's take the last example we did and compare it to this formula. On the problem we did just moments ago, we could compare that to this generic formula here and realize, this is just the problem where m is 10 and p is -4. And if I were to plug 10 and -4 into my formula and do a lot of ugly algebra, which I didn't show here, eventually we would get the same two answers, the same solutions that we got to that specific problem. And so this formula is a generic solution to the equation on the left where m and p can be any numbers whatsoever. And so now what they had essentially done at this point is solved every equation of that type by creating a formula that would lead us directly to the solution without us having to go through the whole process. So we could use this formula to solve the problem we did. We could use it to solve this problem, or this one, or this one, or that one, or anything that has an m and a p but otherwise matches that format. So whatever specific numbers m and p are, we could use this formula to solve it. But then a new problem entered the scene. And what happened was, problems arose where the number in front of the x squared, this lead coefficient here, was something other than blank or a 1 as it had always been. And so the next question that they had to grapple with is, what do we do when that number there isn't a 1, such as a 7 in this problem? Well, somebody had a bright idea. They said, okay, why don't we divide the entire equation by 7? And that would give us the 1, or the blank, in front of the x squared. And then we could use this fraction for m and this fraction for p and use the formula in the upper right corner of your screen. Well, there's absolutely nothing wrong with that, except plugging ugly fractions into that formula just makes there be fractions inside of fractions, and it gets pretty messy. And while it's valid, nobody wanted to deal with that. Too messy. So this was the next historically bright idea that they had. Some mathematicians said, what if we came up with a generic formula for this equation where a, b, and c could be any numbers? We saw in the previous example that a was 7. And they wondered, could we mimic the process or somehow use this previous formula to our advantage here? So some people who had a bright idea, they said, well, let's divide the entire equation by a. And what that does is that gives me an ability to solve this, because they took the previous formula that they had, and in order to apply it to this particular situation, all they needed to notice was that they could substitute the fraction b over a in for m and c over a in for p into the formula that they had created for quadratic equations with a 1 in front of the x squared. Now plugging those in makes for some really ugly fractions. What they did next, and I didn't show it here, but they did some algebraic manipulations and simplifications, and they turned that expression into this one, which may not look exactly the same, but algebraically it is the same. Now I didn't show the algebra, but it is something that they did do. And what then occurred is they had a generic solution. No matter what numbers were in the A, B, and C slot, they had a generic solution or formula to solve a quadratic equation by just plugging that A, B, and C into the formula that you see in the upper right corner. That formula, by the way, is called the quadratic formula. And that's the origin story of that formula. And that completes the second of this 4-video series.